Okay, Bismillahirrahmanirrahim. We continue with this lecture. We were explaining to you the equipment that are being used for conducting the CBR test. One more thing that is being used while testing the soil sample is the use of surcharge weights. What is a surcharge weights? Normally in pavement design, not normally, actually in a pavement design, we don't consider the dead weight of the pavement. This because while testing for the soil, we already assume surcharge weight as a dead load of the pavement. So that's why we have, so even though we have a cylinder of 5 into 7 inches, 6 into 7 inches, but we have used the weight 2 inches. We have spread the sample 5 inches, and the rest of the place in the cylinder was kept for putting the surcharge weights. So surcharge weights not only simulate the weight of the pavement, but when we are testing the pavement, or we can simply say inserting the pavement, inserting the piston in the test sample, these surcharge weights prevent sieving up of the soil sample around the piston so that the test is properly conducted. One more thing about CBR test, even though CBR test can be performed with or without soaking, but for a pavement design, we select only soak test because the soil conditions are critical in a wet condition rather than a dry condition. So even though the soaking, even though unsoaked sample can be prepared, can be tested, but the pavement design engineer only interested in soaking sample of the soil. There is one more thing that is needed to be reminded or needed to be taken care is we soak the sample for 4 days, and for 48 hours we take the swell reading. If the soil is swell, if the soil has a shrinkage problem, this soil may not be tested because there is no use if the soil is swelling soil. That's why before testing we soak the sample for 48 hours. For 96 hours, and we take the swell reading at 0 hour, 1 hour, 2 hour, 4 hour, 8, 12, 16, 24, 48, 72, and 96. Once the soaking period is over, we just take out the sample and put it in the cylinder, like the test of shown, that like the test cylinder shown in this here. Now, if we look at this test setup, we can see this cylinder is placed and it contains the sample and tested in a machine. This is a loading piston, as you can see over here as well. And since we cannot see the soil sample, we just assume that this piston is in complete contact with the soil sample. These are surcharge weight. These are the transducers, or you can have a dial gauge typically to know the penetration. And obviously, the load that is being applied is recorded from a load cell somewhere here. Now, what happens is that once you prepare the sample and allow the test, obviously the tests are conducted and the readings are noted for penetration versus load versus penetration of the sample. Now, once this has been done, we draw a graph versus penetration versus load. It can be penetration versus unit load as well. Unit load is simply you have to divide that load by 3 inch square, as we know the load area of the piston. Okay. Let's see what happens to this curve. You know, we can have 3 types of the results that we can obtain typically from this test. Or you can see 3 curves. Let us look at this first curve. Here, we can see as the load is increases, obviously the penetration is increasing up to this point. And certainly there is a change in penetration, but there is a decrease in load. And at 0.2 penetration, again, we can see with increased penetration, there is increased load. But again, although there is a slight increase in load, but we can see that this is something erratic behavior of the sample, and it is understood the load required for penetration will keep on increasing until the sample fails. If this would have been that after 0.26 there is a load here and there is a load, then there is a load that is increased here, then we could have understand the sample has failed and that would be accepted. But now, on the sudden failure with certain decreased load, and then there is a increase in load with penetration, this is simply unacceptable. And this may be error due to the noting of the reading, and this error cannot be corrected. And the sample testing, the results obtained from such sample can be purely discarded, and we say that the sample we have to test the sample again. In other words, there is no correction can be applied, and conversely, and we can safely say this curve is a wrong curve, and this cannot be used for extrapolation of the results of this sample. Now, the second curve, that is a blue curve, as you can show, represents true behavior of the soil, in which the load is kept on increasing until 0.5 inch. It may be noted that there are subsoil samples that may fail before 0.5 inch. For instance, can fail at 0.3 inches, but then obviously there will be always a decrease in load resistance. Curve will be have a peak and it will fall down. So this is a very correct curve. What we call this is standard curve. This is an ideal curve that is required for getting the true values of CBR. Now, if you look at the third curve, we can see that the load is increasing with the penetration, but in the first few readings, there is a lean curve, and then the curve is changed its shape, and it's similar to blue curve from this point on. So what does this mean? Is that there's something wrong at the start of this test. This can be attributed to two things. One is, as we can see, that this sample is invisible, and we are not sure whether the piston has touched the sample. So before taking the actual load, it cannot be validated. That's why when we start the test, there is a zero error. So this is because this curve is lean because of zero error. And the simple reason may be that the soil has not touched the sample before we have started, when we started the test. The second reason is, when we when we prepare the sample, we have a spacer test, and then 2-inch spacers, and then we start preparing the sample. And what happens is that, since all the first layer received more impact, and all the moisture content from the subsequent layer may have settled at the bottom of this layer. And since while testing, we have done the upside down, so the first layer we have, we are testing. This is the upside down of the cylinder for placing the load. So there may be some moisture content that is available. So when we first start loading the sample, the first layer may have a weak soil because of the wetness or something. So that's why we may have this linear curve. In order to correct this curve, we simply draw a tangent, and when draw a tangent, the zero is corrected. Now, the corrected zero has shifted from its original zero, as you can see in this figure. So, if we are looking at the 0.1 penetration, the 0.1 inch penetration has shifted because of the shift of zero. So, the unit load, if we have we have not applied the correction, the unit load is 100, but after correction, we can see the unit load has increased to 250. So that's why this correction is very important to get the true results. Now, the formulation. Once you know the load, the standard, you have to divide that by 3000 for 0.1 inch penetration. If you are taking the real pounds, or 4500 for taking the value for 0.2 inch penetration. Or if you're taking the unit load, obviously it can be 1000, and then it will be 1500. You must be wondering why there is no direct relation. For instance, if there is a 0.1 inch penetration, the load required 3000, and for 0.2 inch penetration is 4500. Why it is not 6000? It's because the when we start the test, there is a seating load for the piston that is required, so it gives you more resistance. And then once the sample gets seated, the piston make its place, then it will easily penetrate. So that's why we need less load for 0.2 inch penetration than 0.1 inch penetration. Now what you do, you simply find CBR by load obtained from the graph for 0.1 inch, and then load required for standard rock, that is 3000, if assuming I am using this unit, and you multiply by 100. So this is the CBR value. Normally, when we write CBR value, or we take CBR value for pavement design, we don't use this 100. Simply, if CBR is value 25, though it is 0.25%, but we don't take this as 25. We tend to ignore that division by 100 while we take this load. This is a general practice, and it's being all used. One should let me remind you that one thing you must remember, that the soaked values should always be used, not the unsoaked values. Now, we take CBR at 0.1 inch, and we take CBR at 0.2 whichever is greater gives you this design CBR value. Why there is a disparity 0.1 and 0.2 is simply because of that seating load or for the bigger, maybe we may not have estimated the 0.1 inch penetration accurately, even though with application of glass. So it's, if 0.1 inch is higher, take that value. If 0.2 inch there is higher, then take 0.2 inch. But normally what we do, we don't take it as granted. We test 5 samples, and if 0.1 inch value is always greater than 0.2 inch value, that's okay. But if it is 0.2 inch value that is greater, then we take that 0.2 inch. Otherwise, our preferable value is CBR at 0.1 inch value because it gives you the true representation of CBR. Another thing is this influence of moisture upon CBR. As you say, that more the CBR moisture content, the less will be CBR. So it's very important that when you perform a CBR test, that should be done at optimum moisture content of that soil sample. And again, let me remind you that optimum moisture content is for maximum dry density obtained from modified problem test. Let's move on. Another test to soil, to test the soil is the resin modulus test. Now, resin modulus is the latest test protocols that are needed, especially for the pavement design of highways using H2 method or asphalt institute method. Now, what is a resin modulus? It is an estimate of its modulus of elasticity under repeated axial cyclic stress of fixed magnitude load dilution cycle during a test of cylindrical specimen. How this resin modulus is different from elasticity modulus? The main difference is elasticity test is a unidirectional test. We apply the load in one direction and calculate the strain in that direction. But the resin modulus, we can say it's a 3D loading system, in which the load are applied to every axis, and this deformation is also measured in all the axes. And then we divide that load or that stress to the given deformation, and that's called a resilient modulus. And if you look at the real meaning of resilient, it's the modulus, it's the intrinsic property of material to survive the loading during actual condition. Because this when we design a pavement, it's a cyclic load. The vehicle comes, the load passes, the wheel move on, and that's why this test accurately simulate the actual field condition. How it is different again from CBR test is simply the way the test is being conducted. Obviously, the main difference is that even in CBR test, we applied a unidirectional loading, or we can say the load in the Z direction. But in this case, we apply the load in all the directions. The second difference with the CBR test is the is the way the load cycle is applied. The CBR test, we keep on applying the load till the failure of the soil is achieved or it reaches a 0.5 inch penetration. While this resilient modulus, we apply the load for some duration, then we remove the load and let the sample retain its original shape, and then we apply our load. So this is the main difference. Now, this specimen is subjected to a static confining stress, stress provided by a triaxial precision. It is a cyclic version of a triaxial compression test. Those of you who already have the soil mechanics course at the undergraduate level would fully understand what is this triaxial test, and they who have actually performed that test in the laboratory as well. So if you look at the mean resonant modulus, so we can say it's a stiffness of the material at the repeated load. It's a modulus, and modulus is always stress over strain. So this is nothing new, except that this soil, this test is the measure of deviated stress of all recoverable strain. So what is a recoverable strain? We can understand the soil is not a perfectly elastic material. What is a perfect elastic material? A material when the loads are applied, and then when the loads are applied, it goes to deformation, or it is being stretched after the application of the load, and when the load is removed, it simply comes back to original position, or all that deformation caused is lost when the load is removed. This is a perfect elastic material. We can say like steel or like a rubber. But this is not the case with the soil. When we remove the load, after some time, not all the deformation is recovered. And that's why some of the sample goes to permanent deformation. And it keeps on repeating every cycle of a load. Because if, again I say, the soil is not a perfect elastic material. We can say a soil, it can be elastic, plastic material. Since plastic means some of it will go permanent deformation after application, after removal of the load. So that's, and as an engineer, we are not interested in the dead deformation. We are interested only the strain that is recovered. That's why it's a deviated strain. Now, why there is a difference between why this deviated stress is sigma 1 minus sigma 3? Because all the loads, sigma 1 and sigma 3 has a different direction. That's why we have to, sigma 1 has deformation effect, and sigma 3 will have other effect on the soil. That's why the difference of the two stresses divided by a recoverable strain is the resonant modulus. It's the unit of resonant modulus, same as last model. That's pound square inch of megapascal or kilogram per centimeter square, or Newton per millimeter square. So this resonant modulus determines the load carrying capacity of the material. Not only this test is applied for the soil, but it also applied for hot mix asphalt as well. It's a repeated triaxial test, and it is now very widely used in the flexible method of pavement design, especially ASHTO or asphalt institute. Let's look at this test setup. We can see this frame. This, you can say, this is the UTM, in which there is a loading piston. You can see the sample in gray. These are the plates that are restraining it from the movement. And here we, fix some LVTTs to measure the deformation, not only vertically, but the horizontally as well. These are the cliffs. This is a top platen, this is a soil sample, the bottom platen, and then there is a road, there's a chamber, and in between this gap is filled with water. So when the load is applied vertically, the sample, the other load is applied through water all around. That's why we call this a 3T load. And this is the load cell that measures. And then this is cell pressure. We control the pressure inside this chamber. And this is an external LVDT that gives you the overall deformation of the soil in a longitudinal direction. And this is a loading system. Now, what happens is that we keep on applying the load at certain time, and then we remove that load. And once this cycle, this is one cycle, then we start again applying the load. What happens is that, if we plot a strain versus time, as the load is being applied, we'll have a sample keeps on deforming with time, and when the load is removed, the sample tries to recover. But unfortunately, since it is not an elastic material, the sample will not recover fully. If the sample would have, if this would have been an elastic material, the sample would have gone to that position once again. But as I said, this is not a perfect elastic material. Some of the strain is lost at each cycle. We call this the plastic strain. And obviously, there is some load, some deformation is recovered that we call the strain, or we call the recoverable strain. So, time, simply these graphs tells us the time dependency of strain under constant stress. It can be plastic or elastic, degree to which material can rebound or recover strain after removal. So this we call another example of viscous material that deforms with the stress at a time. Now, this is another simulation. What you do is you apply the load, and then there is a rest period, and then we apply the load, and we can find this load versus deformation curve by applying this load. Obviously, strain is changed in length per the unit length. Again, what happens is that we applied the load, the sample recovered this point, we again applied the load again. As we keep on applying the load, we have accumulative strains, plastic strain that is going to increase after each removal of the load, and the rest is the recoverable strain that we are interested in. So this point where this sample has completely have not returned is what we call a plastic strain. So, to brief our session, the result modulus is simply geometric stress divided by recoverable strain. What are the applications? Provides a means of characterizing pavement structural materials, including surface space and materials, surface materials under a variety of temperature. Stress that simulates the condition of pavement subject to load. The test provides an excellent means for comparing the behavior of pavement construction materials under a variety of conditions, moisture, density, gradation, stress. This is how this is a design MR value, or in other words, if you have designed a pavement, we don't take one CBR value, we take representative of CBR value. So this is a design MR, and this will be covered detailed in the class. Another relation that is important is that if you know the elasticity modulus and modulus of subgrade, you can calculate the elasticity modulus of base and subbase using this relation, where you can see this E3 is the modulus of subgrade, 0.2 composite modulus, E2 is the composite modulus of subbase and subbase, and H is the height of the granular. So that's how you can find the values of resonant modulus of other material if the resonant modulus of soil is known to. This relation is old relation. Normally we use E is equal to 2,555 asterisk CBR raised to power 0.25 for all types of soil. This is what happens during a test. If you perform a test and draw the graph, you will have two types of relation. Relation for coarse grained soil will be different from relation from fine grained soil. So if you are testing coarse grained soil, the resonant modulus simply K1 times theta raised to power K2. But K1 is the slope intercept and K2 is the slope intercept. And theta is the bulk stress. So if you draw a graph between log of MR to log of theta, the resonant modulus can be evaluated from this relation. Normally what you do, you have before performing a test, before starting the test, you condition the sample. What you do, you keep this sigma 3 constant for 5 psi, and you find you applied repetition of layer for 200 psi, 200 and 200, and you kept this sigma d to 5 psi. And then similarly for 5 psi, you keep this 5 psi and increase the dielectric stress to 10 psi. Again, the number of repetitions is 200. Then you increase this sigma 3 to 10 psi, test 10 psi, and apply load for 15 psi. What is the sample condition? If sample conditioning is the process in which before testing the sample, you customized your sample according to test. Otherwise, you cannot take the readings at once. You have to condition the sample first and then start testing. So you condition a coarse grained sample, granular sample. You condition the sample at 3 pore pressures, 5 psi, 10 psi, 15 psi, and you can derivative stress at again 5, 10, 15 psi for 200 cycles. So at least before conducting a test, you have actually 1200 repetition of the load before applying the test. So once the sample is conditioned, what you do, you kept the pore pressure to 20 psi and take the reading at 1, 2, 5, 10, 15, and 20 psi. Then you decrease the pore pressure to 15 psi, sigma 3 pore pressure applied from the water that is present. And then 1, 2, 5, 10, 15, and so long, and so what is given in this thing. So once you are done away with this test, you stop this test. So you can say that a total 1200, 1400, 1600, 1800, 2000. So normally after 2200 cycles of load, the test stopped. We have a different behavior when test a nonlinear material, in which what you do for a nonlinear material, we have the slope intercept K3, and then the slope is decreasing. Unlike the coarse grained material, the behavior of coarse grained material is opposite, and you can see that the slope is being reversed. So this is the the behavior, and this is octahedral test, as you can see from this relation. So this is K3 T octahedral K. Again, as against pore grain test, we only sample the condition at 1 pore pressure and 5 diametric stress at 200 cycles at heat, and then we start testing with 1 psi and we stop testing at 10 psi and take the values at different pore pressure. Unlike this test, we have pore pressure we varies and we take the value at diametric stress, while in fine grain we kept diametric stress constant and we varies the pore pressure. This is how the test between two samples are different. Those of you who doesn't know what stress variant is, simply addition of all the principal stresses is bulk stress, and it also sometimes to the weight of their system. Gamma is the weight of the soil, Z, and 1 plus 2 times the. This is the test sample we will perform in the class, and it will be explained. And the combined stress development can be get from this relation. As I said, how the behavior of coarse grain soil is opposite to the behavior of fine grains. This is the same for the moisture content. Comparison of this value. CBR test for sand. We have CBR 31. This equation, this becomes the relation between CBR and MR value. This is 46,500. Shake 20 and 30,000. As you know, have more CBR, considerably more values, and this is evaluated for as fault distribution. And since we this test is very costly, so most of the time people use do the soil sampling by CBR and then convert this to resonant Modulus. So previously we used to have this 1500 CBR. Now this has been replaced by 2555 CBR 0.64, where you don't take the CBR value in person. Be reminded that if CBR is 10, take 10, don't take 0.0. And it's the most common relation used nowadays. So the soil that has got higher CBR values is rated a good soil. And as a pavement engineer, we are comfortable if the soil values are at least 10. We are also comfortable if if it's more than 5, but it is less than 5. It's a poor soil, and it is to be taken with a great care. So this is how you can, there's another table giving you how this MR values is related to uniform soil classification system. So CBR for CH soil is between 1 to 5. For poorly graded sand, can be 15 to 30. And again, A1 soil is a very good soil, having a very good CBR value. A3 soil or A4 soil, as a highway engineer, we are comfortable with A4 soil. It's a very good soil. But we are, very less interest in A76 soil or A75. So to conclude, the properties of subgrade layer influences the pavement performance significantly. These poor subgrade layers can result in severe pavement distresses. Distresses can be prevented or delayed by adopting adequate procedures during pavement construction. So this now ends my lecture. I hope you have fully understood the concept of rendering models. In the next lecture, we'll explain you the plate loading test.